Hi everyone. I know I said I wasn't going to make a video for the next Unit 7 suitability analysis until next week, but this lab's pretty involved, so I thought I'd better sit down and make one and put it on Moodle before next Monday. Like I said, this is a bit of a complicated lab, or probably the most complicated one we've done so far. We're going to be using both raster and vector data, and it's kind of a fun lab though. Doing suitability analysis is kind of fun, I think. And what we're doing is, in this particular example, we're going to use GIS to estimate the locations of, or where landslides would be more likely to occur. And I guess the project area for this is a place called San Bernardino, California. I don't know if any of you have been to San Bernardino, the southern part of California, but there's some factors that of that area that allow itself to be susceptible to landslides. One of them is, well, we'll talk about that later, and actually I'll save that for the discussion that's on Moodle. So we'll get into that. I'll let you guys get into that on Moodle. But again, this is kind of a complicated lab, so let's get started. And I'm just going to go through the lab basically, and then you guys can attempt it on your own in the next 2 weeks. So again, what we're looking at here on my screen, I've got the aerial or the world imagery loaded. I've loaded in the data that I gave you guys on Moodle. I've got SBDEM, so SB stands for San Bernardino. A DEM is a digital elevation model, so this is a raster set that shows elevation, and I'm just going to go ahead and zoom into this right now. So here we have California. San Bernardino is down here east of Los Angeles. And I'll show you what this DEM looks like. So here's San Bernardino. Here's sort of a mountainous, hilly area to the north of San Bernardino where they get a lot of landslides. I'm going to zoom in a little more here. So here's an example of a DEM. Obviously, the lower elevated areas are in black, and the higher the elevation, it goes to gray, and the highest elevations are in white. So remember, a DEM is raster data. Raster, as we have learned, is made up of cells, okay? This particular DEM, the resolution, if we right-click on this DEM and go to Properties, and we go to the Source tab, we can see this DEM is 10, X is 10, Y is 10. That means it's 10 units of something by 10 units of something. And to figure out what those units are, if we scroll down to spatial reference, the linear unit is in meters. So this is what we would call a 10-meter DEM. So each cell occupies 100 square meters of area out in the real world. So this is what we would call a medium resolution DEM. It's certainly not the best that's out there. You know, it'd be better obviously if we had a 1-meter DEM or a 5-meter DEM. It's certainly better than say a 30-meter DEM. So 10 is what we would say would be medium resolution. If you notice these numbers here, so low 335.3, high 1968.3, that is the elevation above sea level in meters. So if those numbers look weird to you, that's because those numbers again are in meters, and if you wanted to put those in feet, you could just multiply them by 3.28, as there's 3.28 feet in a meter. Some other pieces of data, I'm just going to shut the DEM off for a second. We've got some burn data. Now this burn data was collected after a fire that happened up in the hills. By the way, this data and this lab was made by Esri, and this burn data was collected, I believe, back in fall of '06. I think, as there was a huge fire that went through this area. And we'll get into more of this burn data and why there's different polygons in the burn data here. But as we're going to see, some polygons, they categorize these polygons by how badly they were burnt. And we've got low burned areas, we've got medium burned areas, and then we've got high burned areas. And we'll get into that here in a second. I'm going to turn off the burn data. We have the California state boundary in here. We don't need that on anymore. We've got a stream layer here of the San Bernardino area. We've got a roads layer. So these are all the roads that are up in that area. We've got a fault layer. So these are the faults. Obviously, if we identify some of these faults, the major fault, as we all know, that runs through California. I think one of these, pretty sure one of these is the San Andreas. Not sure which one. Okay, yep, there we go. There it is right here, running right along the edge of this hillside. So the San Andreas Fault. A little bit of geology in there. And we've also got the location of several schools, which if you worked for the school district or if you worked for emergency management, you would probably want to know where these schools are located in case landslide, in case you were in case the conditions were right for landslides. So that's the data we're working with. The thing that I want you guys to know about suitability analysis is, generally speaking, you can use both types of data, raster and vector. And right now, the only piece of raster data that we have is the DEM. Okay, everything else is vector, points, lines, and polygons. Okay. But normally when you do suitability analysis, eventually the data that goes into your analysis all has to be turned into raster data. Okay. So we've got the SB DEM, that's raster, everything else is vector. Okay. So what the lab goes into is using GIS data to figure out where these landslides can occur. And there's three factors. Obviously you could use more, but the three factors that this lab uses is obviously slope. You need slope for a landslide to occur. So that's one of the pieces that go into our analysis. The other piece we're going to use is aspect, and if you haven't heard of aspect before, what aspect is the direction that a slope faces. Okay, so the direction that a hillside faces: north, south, east, west, northeast, northwest, southeast, southwest. So there's 8 cardinal directions that a slope could face. Okay, and then the last piece of data we're going to use in our analysis is this burn data. Okay, and what we're going to say is the areas that were more severely burned have a higher probability that a landslide is going to occur on them. Okay, so again, the three factors we're going to use: slope, aspect, and the burn data. And obviously, when you're looking at landslides, you could probably look at some other factors, maybe geology, maybe these faults here that are on the map would play into it. But those are the three that we're going to use. So I'm just going to kind of go through these three one by one, and I'll show you how this analysis is going to work. So let's start off with the DEM. And from the DEM, we're going to create our slope data and our aspect data. So, and I need to pull the lab up, and I just realized at the bottom of my screen here I don't have the lab pulled up. So I'm going to pause the recording here for a second and pull that up so we can kind of go through it. Okay, I've got the lab pulled up, and I can't exactly remember where I left off. Sorry about that, but I think I was explaining to you we've got raster and vector data. The three factors we're going to use in our analysis: slope, aspect, and the burn data. So the first thing, let's deal with our slope data. And slope is going to come from the DEM. The GIS has a tool or the ability, if you have elevation data, it can calculate the slope and the angle of that slope in either degrees or percent slope. Okay? So to do that, I'm going to pull up the slope tool. Now we're going to need the spatial analyst extension for this, and at home on your computer, make sure the first thing you do is go to Customize up at the top in ArcMap, go to Extensions, and you need to make sure Spatial Analyst is checked on because we're going to be using the tools that come with Spatial Analyst, okay? So again, make sure Spatial Analyst is checked on. Then I'm going to open up my search window. And I'm just going to search for the slope tool. So I'm just going to type in slope, hit enter. And there's the one we're going to use is slope spatial analyst. So I'm going to click on that. So here we go, input raster. Well, the slope comes from the DEM, so our input raster is going to be SBDEM. We need to tell the GIS where to save this new piece of data, which is going to be slope. So I'm going to hit my browse button. I'm just going to make a folder on my desktop. You guys are going to want to make a folder probably that says Unit 7 or something, wherever you guys save the data that you work on throughout the semester. Again, I'm just going to make a Unit 7 folder on my desktop here. And I'm just going to call this SB for San Bernardino, and I'm just going to call it underscore slope. So SB underscore slope. Now again, we can have our slope data be in degrees, or we can have it be in percent rise. Okay, so in other words, rise over run, and to get a percent, you would multiply that by 100. Okay, degrees is a little better to understand, easier to understand. That's what the lab calls for, is to put your slope in degrees. So let's use that option, and let's click OK and run the tool here. Might take a little bit for the tool to run. So it's got quite a bunch of data to calculate through here. Again, we're working with 10 meter cell sizes. Hopefully it's working. Yep, here we go. Okay, so we've got some psychedelic colors here going on, but as you can see, we've got our slope data now. If you look over in your table of contents, the green areas go between 0 and 4.7 degrees. So 0 would be flat, okay? And the highest degree of slope we have, which obviously would be up in the hills or the mountains here, we have 80.9 degrees. Just to give you some reference here, 0 degrees would obviously be flat. A 90-degree slope would be a cliff that's straight up and down. Okay, so hopefully that makes sense. So 0 is flat, 90-degree slope is a straight up and down cliff. Okay. All right, so we've got our slope data there. The next thing that the lab calls for us to do, and I'm not going to go through the lab step by step. The next thing we need to do is make aspect data. Okay, and that comes from the DEM again. So I'm going to pull up my search tool, type in the word aspect. Now again, what aspect is the direction the slope faces. okay? So type in aspect, hit enter. Again, we're using Aspect Spatial Analyst. Our input raster is going to be DEM. Output raster, I'm going to tell it to save it in my Unit 7 folder, and I'm just going to call this SV underscore aspect. Click Save. Click OK. Let the tool run. Let it draw here, and we've got some more psychedelic colors here. But if you look over at your table of contents, you can see now we have the direction that slopes face, okay? So if it's a flat slope, obviously that wouldn't be a slope, but if it's flat, it's attributed with a -1. And then north-facing slopes are between 0 and 22.5. So what that 0 to 22.5 means is degrees on a compass, okay? So obviously 0 and 360 is north. Let's think about this. 90 would be east. South is 180. West is 270. And then we're back to 360 at north, okay? So that's what these numbers mean right here. So north-facing slopes go between 0, or actually 337.5 degrees to 22.5 degrees. And then you've got northeast, east, southeast, south, so on and so forth. Okay, so the different colors represent the different degrees on a compass that the slope faces that direction. Okay, so that's aspect data. Final thing we need to do is we need to deal with this burn severity data, okay? Now I'm going to turn off my aspect and slope and DEM, and I'm going to turn on the burn severity shapefile. So you can see here we've got a polygon shapefile, which is vector. Remember, the DEM, slope, and aspect are all raster data, okay? The burn severity is vector data, and it's in polygons, and these polygons were I'm not exactly sure how they were collected. One way you could collect these polygons is after the fire. You could go out with a GPS unit and GPS all of these different polygons where the fire burned. You could also use a plane, take an aerial photo of the burnt area, and then digitize the areas that were burned. Okay? Let's open up the attribute table for the burn data. So right-click on the burn severity, open attribute table. You can see here there's quite a bit of data that we're looking at. You guys can look through this as you go through the lab, but the one thing that we're interested in calculating areas that are susceptible to landslides is this column that's called Veg Burn Sev, and what that stands for is Vegetation Burn Severity. Okay, and as you can see, there are polygons that were low, moderate, or highly burnt. Okay. Now remember what I said with suitability analysis. You can use vector and raster data, but eventually everything has to be turned to raster data. This burn severity data is vector data, so what we're going to do with this right now is we are going to convert this to raster data. All right. So the tool we're going to use for that is we're going to open up the search tool. We're going to type in polygon to raster, because these are polygons and we want to convert to raster. So I searched for that tool, the third one down, polygon to raster. It's a conversion tool, so we're going to click on that. Our input feature is going to be the burn severity data. Now for value field, you need to remember the difference between raster and vector data is vector data can have an attribute table where it can house all of this information about the point line or polygon. Raster data can only have one attribute, and that attribute goes with the cell that's in the raster data, okay? Now if you remember, the one attribute that we're concerned with in this case is that veg burn severity column. So for our value field here, we need to make sure and pick that column because that's the data that we want to carry over when we create our raster data. Okay? Again, I need to tell it where to save it. I'm going to hit my browse button. I'm going to call this SB burn RAS for raster. So San Bernardino burn, and it's a raster data set. The final thing you need to do here is we need to tell the GIS, okay, what cell size do we want this raster data to be? And if you remember what the first piece of raster data we were working with was the DEM, and if you remember, it was a 10-meter DEM. So we want our burn data to be 10 meters as well, okay? So we're going to put in 10 for the cell size, okay? Okay, let's click OK. All right, and if I turn off the burn severity, now you can see we have a raster data set of those same polygons. Let me turn back on the shapefile, and I'm going to make it hollow with an outline so that we can kind of see it. Okay? And as you can see, we told it to use that veg burn severity category. All right? And it kept the low, moderate, and high. If you open the attribute table for that new raster data set, you can what it tells you here is the low burned cells. There's 347,020 low burned 10 by 10 cells. There are 773,071 moderately burned 10 by 10 cells, and there are 151,870 highly burned 10 by 10 cells. And the GIS gave it a number to represent the low, moderate, and high. Lows are represented by a 1, moderate by 2, and high by a 3. Okay? So that's what's going on there. And if we zoom in, if we just zoom in on a piece here, I just want to show you the difference between a raster and vector data. Okay? So you can see here, here's the vector data that what we had originally, this line, and here is the raster data. You can see those 10 by 10 cells. That's why it's square shaped, okay? And think about this a little, and one of the discussion points I have in Moodle is what is the error when you convert between vector and raster data? So hopefully when you look at this picture here, you can see that, or maybe think about, well, what is the error when you convert between raster and vector data? Okay, so think about that, and that's one of the things I want you to discuss in the discussion for Unit 7. All right. Let me zoom back out here. I'm going to clean my map up a little bit. We don't need the burn severity data anymore. I'm going to remove it. And we don't need this DEM anymore. I'm going to remove it because we've created the data that we need from those two data sets. So if we don't need them anymore, I like to get them out of my map. Remember our 3 criteria: slope, aspect, burn data. And remember what I also said. You can use both vector and raster data in suitability analysis, but eventually everything has to be in raster. And lo and behold, our 3 criteria are all in raster. We've got slope in raster form, we've got aspect in raster form, and we've got the burn data in raster form. Okay? And I think the lab is going to have us deal with the slope first. So if we look at the lab here and we scroll down, I'm going to skip some stuff, but I'm going to go, let's deal with our slope data first. Okay, Now if you read through this lab here, the way we're going to do our analysis is we're going to rank the areas between 0 and 6. 0 being areas that are not susceptible to landslides, 6 being areas that are highly susceptible. Okay, so this is I guess what you would say a subjective analysis. Again, anything that's 0 is we feel like if an area is attributed with a 0, it cannot have a landslide. Any area that's attributed with a 6 can. Okay. Now what we need to do is reclassify our slope data. And there's a table here that tells us how we want to reclassify it. So any slope between 0 and 5 degrees we think has 0 chance of having a landslide, so we're going to give it a 0. And we feel the same way with areas between 5 and 10. Now 10 to 15 degrees slope, we're going to give it a 1. So it has a slight chance of a landslide. 15 to 25 degrees slope, 3, so a little bit greater chance. And then 25 degrees to 81 degrees, we're going to give a 6. So we feel that between 25 degrees and 81 degrees slope, that has the greatest chance of having a landslide. Okay, so we're going to give it a 6. So let me show you how we're going to do that. So we're going to take our slope data and we're going to reclassify it. So I'm going to search for the Reclassify tool. So Reclassify Spatial Analyst. Our input raster is going to be SB Slope. And I believe if we look back to the lab wants us to do natural breaks, 6 classes. Okay, so we're going to hit the Classify button. We're going to do natural breaks, 6 classes, and then we need to put in the different break values over here in this box here. So the first break, so we've got 5, 10, 15, 25. So 5, 10, 15, 25, and then I think the next one was 33, and then the next one is just 81. Okay, so those are our break values. Now we need to go in and give it what we think each of these different levels of slope, the chances of it having a landslide are. Remember we said 0 to 5 degrees, no chance, so it gets a 0. 5 to 10 degrees, we think no chance of a landslide, 0. 10 to 15, some chance. Remember, we're going to give that a 1. Again, I'm getting this from this table right here. Okay. Let's see, 15 to 25, a 3. And then 25 to 81 is going to get a 6. And this one's already a 6. All right. Going to tell it where to save this. I'm going to call this SB slope, and then I'm going to put an underscore RC to let myself know that I reclassified it. Okay. Again, we're taking the slope data, breaking it down into different classes, and telling the GIS the probability that we think each of these slope classes has of having a landslide between 0 and 6. Okay. Click OK, let the tool run. Okay, here we go. As you can see here, we've got 0, 1, 3, and 6 areas that have 0 chance. The flat areas are green, purple areas are 1. Pink areas, moderate chance of a landslide, 3, and then the dark blue areas, I might change that color a little, just to maybe some kind of red here. Red areas have a good chance of a landslide, which is a 6. And you can see this makes sense. Flat areas are down here where the city is, red areas are up here in the mountains or the hills. Okay. Now, I've taken my slope data, I've reclassified it. I want to remove that slope data, clean my map up. I no longer need that slope data, SB slope, so I'm going to remove it. Okay. Next thing, I believe the lab has us reclassify, just like we did with our slope, we need to reclassify the aspect data. Okay, and here's the table that we use to reclassify it. Now remember what aspect is. Aspect is the direction that a slope faces, okay? Now Esri made this lab up. I got this lab from a lady in Esri in Redlands, California. She's nice enough to let me use it. Now this is all subjective based on what Esri thinks. You, as a geologist, or if you have a lot of expertise with landslides, you may disagree with this analysis and you would change up the numbers, okay? Her feeling is any slope, if you look at the numbers here, so slopes between 150 and 210 degrees on a compass have the best chance of having a landslide. So you can see 150 to 210 is attributed with a 6 here in this table. Now, I talked to her about this, and what she thinks is south-facing slopes, so the 150 to 210 are south-facing slopes, okay? Her feeling is south-facing slopes get the most sunlight, therefore they're drier, therefore they don't have a lot of vegetation on south-facing slopes, and so if you get a big rain and it starts to wash that soil away, there's no vegetation or root system to hold that soil in place because that's so dry, all right, because it gets the most sunlight. Again, I'm not a geologist. I don't know if this would be true or not. Some of you may know more and disagree with this, but her analysis says south-facing slopes have more chance of a landslide than the others. So that's why in this table the south-facing slopes are attributed with a 6. And so that's what we're going to do here. Again, back in ArcMap, I'm going to turn off our slope data, turn on our aspect data, and we're going to use the reclassify tool again. And we're going to reclassify the aspect data. And I believe the lab says we want to do a defined interval and type in 30 for the interval size value. Okay. So we're going to hit the classify button, defined interval, interval size, we want to do 30. And let's see, now we need to rank between 0 and 6, just like our table says here. Okay. All right, click OK. -1 to 0, those slopes don't face any direction, so that gets a 0. 0 to 30, 0. 30 to 60, 0. 60 to 90, 0. Again, I'm pulling this information from this table here. Okay. 90 to 120 gets a 1. 120 to 150 gets a 3. Now remember, 150 to 210 gets a 6. Those are the south-facing slopes. We feel in this lab anyway that the south-facing slopes have more susceptibility to landslides. 210 to 240 is a 3, I believe. Yep. And then I think what's after that, 240 to 270 is a 1. And 270, what's everything else? 270 to 360 is a 0. So everything else is 0. Okay. Going to tell it where to save this data. I'm going to hit the browse button. I'm going to call this, let's see here. SB aspect. I'm going to put an underscore RC here to let myself know that I reclassified it. Okay. Click OK. Let it crunch through the numbers here. Again, we took our aspect data and split it up into a 0, 1, 3, or 6. Again, south-facing slopes, the pink slopes, those are south-facing. They're attributed with a 6 because we feel like those are the ones that are the most susceptible to a landslide. Okay. I'm done with the aspect data, so I'm going to right-click on SB aspect and remove it. Don't need it anymore. I like to keep my map clean when I'm done with a piece of data and I'm doing this. I like to clean my map up, and anything I don't need I like to remove. Okay. All right. We've reclassified our slope. We've reclassified our aspect. We don't need to reclassify our burn data because if you remember, and we open up the attribute table for it, 1 is low, 2 is moderate, 3 is high. Okay. And actually, I'm just going to click here where it says low and put a 1 here, moderate, just to let myself know that I remembered what these numbers are. Okay. Okay, we're kind of on the final step here, all right? What we need to do is take all 3 of these pieces of data and somehow combine them in our analysis to figure out which areas are susceptible to landslides, all right? And the way we're going to do this is we're going to sort of weight and rank our data, all right? Now there's several ways we could do this, but the way the Esri decided to do this in this lab is they decided to weight the different pieces of data based on their importance, okay? And here's the equation we're going to put into the GIS, okay? So we're going to multiply, or we're going to add these pieces of data together, but each piece of data is going to get multiplied by a weighting, and that weighting has to add up to 100%, okay? In this particular example, in this lab, the slope gets 60% of the analysis. In other words, we think slope is the most important, so we're going to give it 60% of the weighting or multiply it by a 0.6. Aspect and the burn data, while they're important in the analysis, we're only going to give both of those a weighting of 20%. In other words, we're going to multiply those 2 pieces of data by 0.2. 0.6 plus 0.2 plus 0.2 adds up to 100%, okay? Again, slope is the most important. Obviously, you can't have a landslide without a hill. You need slope. So we're going to give it, again, 60% of the weighting. Or in other words, multiply it by 0.6. I know I'm repeating myself here. I just want to make sure you understand this. The other 2 pieces of data are only going to get 20%, or in other words, we're going to multiply them by 0.2. Okay? So the final tool we're going to use here is something called Raster Calculator. So I'm going to type Raster Calculator into my search window. Here it is right here, the second one down, Raster Calculator Spatial Analyst. Okay. It's better as much as you can click all of these numbers in, okay? So we are going to double click the slope data, multiply it times 0.6, add that to the slope data, multiply it by 0.2 because it gets 20% of the weighting, and we're going to add that to the aspect data, and we're going to multiply that by 0.2 as it gets 20% also. And then the lab tells you to name the output for this raster high sus, which stands for high susceptibility. Okay. So I'm going to hit my browse button. I'm going to name this high underscore sus. Okay, our equation's in. We're going to click OK. All right. I'm going to turn, actually what I'm going to do is I am going to remove the burn data. I don't need it anymore. Remove the slope data. Don't need it anymore. Remove the aspect data. I don't need it anymore. What we're left with is the areas that are high susceptible to landslides. Low is 0, which is black. High is 6, which is the white areas. Okay. Final thing the lab has you do is tease out all the cells that have a ranking of 4.8 or higher. We want to get those by themselves. Okay. So we're going to put this equation in using Raster Calculator. High sus greater than 4.8. In other words, we want to pull out all of the cells that have a ranking of 4.8 or higher. Okay. Again, I'm going to pull up my Raster Calculator tool. Double click high sus. Click on the greater than sign. Click in 4.8. And I think, what does she want you to name the output raster highest? Okay. So in our tool, we're going to hit our browse button and we're going to call this highest. Click OK. Don't need high sus anymore. I'm going to remove it from my map. All right, so here we go, the gray areas. And again, your colors might be different when you go through this lab on your own machine. I think ArcGIS just randomly picks these colors, I think. But the blue areas have a ranking of 4.8 or higher. Okay, so those are the areas we feel like in this lab, in our analysis, that have the greatest susceptibility to landslides. Okay. Let's go ahead. What might be kind of nice is if we double click highest and we go to symbology, let's highlight the 0 color and let's remove it. And instead of blue, I'm going to turn the color for the 4.8 or higher to red. And instead of a 1, I'm going to call this high suscept. I can't spell, so you guys can spell better than me. High susceptibility. No idea if that's how you spell susceptibility, but you guys get the point. Click OK. All right. There's our final data. And another thing we could even do is we could double click highest. We could go to display and maybe just make this slightly transparent, like 45% transparent, so we can kind of see the aerial photo behind it. All right. Okay, there's our final map. Now again, the 3 factors we use in our analysis: slope, aspect, and the burn data. We got all of our data into raster form. We reclassified our data based on, again, that's sort of subjective. There's, you or someone else may completely use, maybe they would use a ranking between 0 and 3 or 0 and 10. We used a ranking between 0 and 6. We reclassified our data within those parameters, 0 and 6. We used the Raster Calculator tool to sort of combine the burn data, the aspect data, and the slope data. And now, based on our analysis, these are the areas we feel would be susceptible to landslides. And for your final map, I just want to see those areas. I want you to turn the streams on, turn the roads on, turn the faults on, and I want you to, you'll click into layout view and you'll make your map, and this is what your final map will be. Okay, with your north arrow, scale bar, title, and everything else. All right. So I'm looking here. This video is about 45 minutes long. I don't know how long my others were. This feels like it was probably one of the longest, but this was kind of a more involved lab. So again, call me, email me, come in and see me if you have any questions. I think it would be good to listen to the video, go through the lab, and then probably go through it again to make sure you understand how all of this was done. It's probably might be a little confusing the first time. Again, get a hold of me if you have any questions. But I think if you probably did it a second time round, it would probably make more sense. So hope this video helps. Again, get a hold of me if you have any troubles, and we will see you online. And if you have any questions, pose them in the discussion. That's okay too. Participate in the discussion. One of the things that I asked you to think about is, okay, we made this map. We found the areas that are susceptible to landslides. Who would be interested in a map or data like this? Okay, think about who would care to see this data. All right. Anyway, thanks for the time, and we will talk to you all later. Bye now.